this is another induction problem. There's a uniform magnetic field into the screen, and there's a rod which is sliding over an L-shaped rod in here, and the direction of velocity is basically 45 degrees with the side lengths of the other rod in here. So we would like to find the EMF in that loop in here at time t, and then we would like to compute the current at time t. But this time, of course, the resistance of the loop basically increases with time. So we are just taking this thing into account. So the relevant information is the cross-sectional area of the rods and the resistivity. So by using these, we are going to compute the resistance and the current. So we need to ignore the contact resistances in here. So we are assuming that these contacts are very good. So that's another assumption that we make. So let's then go ahead. This is very straightforward actually, but I'm going to solve it by the methods that we have developed. So these are the two wires. So that distance is Vt, which means, let me raise this, that distance is Vt times the square root of 2. And that distance is also Vt times the square root of 2. And so therefore that distance is 2Vt. All right. So these are the distances. The second thing is I'm going to draw this again in a separate graph. So I'm going to show a direction in here. So let's just choose that direction. I'm going to compute the EMF along that direction. So for this reason, we need to choose an area vector. So area vector would be pointing, in that case, the out of the screen direction. Let me draw it in here. Just keep in mind that these are my choice. You can choose them in the opposite direction. It doesn't matter. So therefore, the magnetic flux is the dot product between the magnetic field and the area. But let's remember that the magnetic field in that case is given as into the screen. So this then implies that that dot product is negative. And so therefore, I can compute the area as the 1/2 of the side lengths of this triangle. So therefore, the flux is minus bv squared t squared. So this is a scalar quantity, of course. So we can see that the flux increases quadratically with time. So that means flux as a function of time has this kind of a dependence. Which means, of course, the derivative also changes with time. So if I take the derivative of that expression, let me continue from here. So the EMF would be then minus the time derivative of the flux. So in that case, that's going to be 2bv squared t. So the EMF depends on time. All right, so let's then pass to a new page. Now I would like to compute the current, which is equal to EMF divided by the resistance. But let's just state this. I'm sorry, I just forgot to state this. So the EMF is positive, so that means it's really along that direction. So that's the direction which is important in here. Okay, so then we would like to compute the current. In that case, I need to find the resistance. So the resistance is equal to resistivity times length divided by the cross-sectional area. So this is more or less uniform cross-section with uniform resistivity. I just need to compute the length. sorry, but the lengths are given in here. So there are these three sides to that triangle, and so therefore the resistivity multiplied with the length, so the lengths are Vt root 2 plus Vt root 2 for the two sides, and for the hypotenuse we have 2 Vt divided by the area. So therefore the resistance increases linearly with time, and it is like this. It is 2 times rho V over the area 1 plus root 2. Let me move this to the front. So let me write it down like that, right? It is 2 times 1 plus root 2 resistivity speed divided by the area times time. So the resistance increases with time too. So therefore the current is 2b v squared t, which was the EMF. Let me check the EMF. 2b v squared t, yes. Divided by the resistance. It is therefore 2 1 plus root 2. Resistivity speed divided by the area times t. So therefore times go away, one of the speeds go away, and so as a result we get like b times v times the cross-sectional area of the wires divided by 1 plus root 2 times the resistivity. So therefore the current is a constant. So that's inside the box. So what's the significance of this? Well, it has no significance at all. It's just a simple observation. But let's just note that the current is proportional to the speed. So that means if the rod is moving really slowly, then the current will necessarily be small. Just as we expect. So in any case, so as a result, we have a circuit in here where this cross-sectional area increases with time, and that's the reason why the flux changes. So therefore, there's an induction in here, but somehow the length of the circuit also increases, which means an increase in the resistance too. So that's just a problem that somehow includes both of these effects.